Okay, hopefully I can get this in one take. So, the problem I chose to do for this discussion problem was Leetcode number 70, climbing stairs, which is a Leetcode easy. Basically, the problem describes you are climbing a staircase. It takes n steps to reach the top. Each time you can either climb 1 or 2 steps. In how many distinct ways can you climb to the top? And so we have to create a function that basically, for any n steps, a returns this value. So how are we going to go about doing this? Well, first, we can actually imagine a guy on a staircase. I'm going to do 5 steps. Imagine this is our guy. So we'll imagine a circumstance in which he goes up, for example, 2 stairs first, then 1 stair, then 2 stairs. So 2, then 1, then 2. This is a valid solution to n equals 5 because we're only using 1s and 2s, and these all add up to a total of 5 stairs. Of course, he can, if I erase this real quick, he can do something like, he can just do, oh my goodness. He can just go up 1 at a time, in which case this would be 1, 1, 1, 1, 1. He can do 2, then 2, then 1. Then 1. There's many ways he can do this. All that matters is that we use either a 2 or a 1, and the total number of steps that we're taking will add up to 5. So let's define S of n to be the total number of distinct ways that we can climb up n stairs. So let's look at an example of n equals, n equals 6. So a way we can kind of phrase this is imagine the most simple solution to this problem, in which case the guy climbs up the stairs 1 at a time, right? I'm going to symbolize this as just 1, 1, 1, 1, 1, 1. Right? Because he's taking 1 step 6 times. So what we can do is we can imagine looking at all the different ways we can kind of clump up this simplest value into solutions, into, for example, taking these two, clumping this into, for example, 1, 2, 1, 1, right? Because this is still valid. It only uses ones and 2s, and it's going to equal, if we sum this up, it's going to equal 6. So we just have to look at all the ways we can kind of clump up this kind of list right here. So we can look 1 at a time, right? We can look, for example, at the first step, right? And we can choose one of 2 possibilities. Either we decide that this first step is going to be a 1, that we're not going to clump up with the next value, that it's just going to be a 1, in which case I'm going to draw in red values that are fixed. So this is fixed. We've determined that that this is going to be a 1. Or what we can do is we can take this value and we can clump it with the next value right here, in which case we've agreed that these 2 steps right here are going to combine into a fixed 2. So we're going to have 2 and then 1, 1, 1, 1. Of course, we still don't know what we're going to do with the rest of the steps, but we've established what we're going to do with either 1 step or 2 steps, right? So then we can zoom in even more. We can look at whatever is unfixed and just repeat the process, right? We can kind of zoom in. How did I zoom in earlier? I'm just going to zoom in like this. We can imagine zooming in and focusing on this section and just repeating the process, where we look at the first one and we choose either to skip, in a sense, in which case we end up with 1, 1, 1, 1, 1, 1, or clump it up, in which case we end up with 1, 2, 1, 1, 1. So if you look at this basic structure, we kind of seen an example of recursion. Basically, once we've fixed one solution, we kind of have a sub-problem, in which case we can repeat the procedure that we did at the beginning. Once we've fixed, we're going to look at this side right here. Once we've fixed this one, whatever we have remaining is just going to be the problem of finding S of 5, right? And we're saying that we're finding S of 6 initially. Once we've fixed 1, what we have right here is S of 5. And over here, once we fix the 2, what we have here is S of 4. So for S of 6, the total number of ways that we can get 6 different steps is just going to be equal to S of 5 plus S of 4. And of course we can, repeat the process. How are we going to get S of 5? Well, if we follow the same structure where S of n is equal to S of n minus 1 plus S of n minus 2, then we can find S of 5 by doing S of 4, plus S of 3. So if you're, mathematically adept, you should kind of look at this basic template right here and think, oh my god, that's just the Fibonacci sequence, right? You might remember from math class that for Fibonacci f of n, that's just equal to f of n minus 1 plus f of n minus 2. So this problem is functionally identical to just finding the Fibonacci number for a given index. And we can actually kind of gut check this by comparing S of n for different values with the Fibonacci sequence. We can just do brute force here. We can make like a table n S of n. Now we know for 0 steps, there's only one way to climb that. For 1 step, only one way. For 2 steps, there's 2 ways. You either do 1, 1, or 2. For 3 steps, you can do either 1, 1, 1, 1, 2, or 2, 1. So there's 3 ways of doing it. 4 steps is a little more complicated, but if you work it out all the different ways, you'll see that you get 5. Same thing with 5. Takes a little bit of effort, but if you compute it out, you'll see it's 8. And you can see that this just follows the Fibonacci sequence. So this is identical to just the Fibonacci sequence. So for a solution, we know how to do the Fibonacci sequence. We've already gone over recursion, so we're just going to do a basic recursive solution. We're going to define our base cases. So if n is equal to, if it's equal to 0 or n is equal to 1, return 1, right? And we're just doing these 2 base cases right here. Otherwise, return climb stairs n minus 1 plus climb stairs n minus 2. And yeah, I actually think is this written in C++? Well, we'll just run this. I think I'm thinking in C++ right now. Okay, it's good. So our example cases are good. So let's submit it and see if it works. Exciting. Uh-oh, it doesn't work. So you'll see here it says time limit exceeded. So what is this problem? There's nothing fundamentally wrong with our algorithm in terms of its accuracy. If we have an integer n, this will give us the right solution. But the problem with Leetcode is that it's not just good enough to have a right solution, a correct solution, but you need to have the best solution possible. You need to have one that's efficient. And our algorithm right here, while it is correct, it doesn't scale very well. If we use super big values, it's going to take a lot of computational time, and according to Leetcode, that doesn't really suffice. It wants us to come up with a better solution that scales better. For this class, that probably wouldn't matter too much because this course is more focused with the accuracy of solutions rather than its efficiency. But the solution to this is rather easy, so I'll still go over it, and we can finally get that success screen. So what's the issue? Well, the big issue here is if we go back to the structure we were looking at, right? We're going to do S5. So S5 splits up into S4, S3. Now, with our recursive format, we know that S4 splits into S3 and S2. And we know S3 splits up into S2 and S1. Well, we know S1 is just 1, so we're good there. We know S2 splits up into S1 and S0. We know S2 splits into S1, S0. And we know this splits into... Okay, I'm not going to continue. You got the idea here. This splits into S1, S0. But if we imagine the actual computer going through this, it's going to go, okay, S5, I need to compute S4, so I need to compute S3, so I need to compute S2, so I need to compute S1. So we'll compute S2, and it computes S3. But then when it goes back to this side right here, when it comes time to compute S2 again, even though we've already established a value for S2, the value might be X or something, it's going to go through the effort of computing S2 all over again. And this stacks up for bigger problems. Once we've spent all this time to calculate, S3, if it has a value of Y, once we go back to this side of the branch right here, once we encounter SY, we're going to go through all this computational effort to compute S3 again, even though we already know it's a Y. So why are we computing it again? We're doing too many redundant calculations. So a basic way that we can circumvent this is using a technique called memoization. Not memorization, without the R. It's memoization. And this has some Latin root or something. It's called, I think it means like to remember or whatever. And so basically, once we compute a value, we're going to map it to a dictionary. And we're just going to say, we're going to keep a log. We're going to keep like a table of all the values that we've computed so far, so that once we're computing a new one, we can briefly check, okay, have I already computed this before? If so, pull from this list right here. If not, compute it and then add it to this dictionary so that I don't need to compute it again. So how are we going to do this? We're going to use a data structure that we haven't exactly gone over in class yet. It's called a hash map. You don't have to worry too much about it, but if you're familiar with like JavaScript or Python or something, it's basically functionally identical to a dictionary, or if you're in C++, it's functionally identical to an unordered map. And it basically just allows us to map a value, we'll say, for example, 3 to some value, y, right? And so we can look for, map of 3 and it'll give us y, right? We're just caching our values. So how do we use a hash map? What we're going to do is we're going to just type in hash map, integer, right? Remember your wrapper classes. We can't just use int. And I'm just going to name this memo. It's going to equal a new hash map. And we don't need to repeat integer because we have our data structures. And so basically how we're going to do this is first we're going to look for, what we're going to do is when we're computing climb stairs and we're going to make sure that we haven't already computed that. So we're going to look in our memo, we're going to get the index at n and see if it exists. If it exists, there's going to be some value there. If it doesn't exist, then when we call memo.getN, it's going to point to null, right? So if we want to assure ourselves that something is there, then we should be saying when memo.get doesn't equal null, which means when something is there, then just return memo. Jesus Christ, I can't type. Memo.getN. Otherwise, what we want to do is we want to do the computation, and then once we're done, we cache our value in the memo and then return it. So we just basically, how it's going to look is we're going to have our solution, right? While I'm here, I'm going to kind of change a little bit of this so it's more efficient. Step one, what I'm going to do is if we look at the constraints here, we see that the smallest value that n can be is 1. So why are we wasting our time looking at n equals 0? Instead, for our initial conditions, we shouldn't be looking at 0 and 1. We should be looking at 1 and 2 because we're never going to be calling n equals 0. So we can save a little bit of computation time. We know when n equals 1, it's 1. When n equals 2 is 2. Otherwise, similarly, we can just say that we'll just return n. However, we're not actually going to do that because we kind of want to, in the world of Java, you kind of get brownie points for keeping your code, by having your code have as little parallelism as possible. If you're using if statements, try to keep them with as minimal code as possible. So what we're going to do is we're going to have int solution, right? And if we enter this, we're just going to say our solution is n. And if we're here, we say our solution is n minus 1 plus n minus 2. And then what we're going to do is we're going to do memo.put n solution. Basically, what this just does is it maps our solution value to the index n, and then we're going to return solution. Now, this is properly implemented memoization. So if I run this, please. Whoops, I made a mistake. So actually, I made a mistake. We should not be putting our memo table inside the function because that just means that whenever we're calling the function, we're resetting memo, which kind of just defeats the whole purpose of memo because that means the table is always going to get cleaned out. Instead, we want this to be kind of a table that transcends the function. So it should be within our class, but not the actual function itself. So now our memoization should actually work. And if we press submit, ta-da, you get 100%. Not only is this an efficient solution, but it's actually the best solution. So awesome.